We'll dive into the first story here, which I made a Taylor Swift reference.
Mm-hmm.
I think this is going to sell more tickets.
It's definitely going to sell more tickets.
And this...
Across the universe.
Across the universe. Headline from CNN, new type of supernova looks like nothing anyone has seen before.
Yeah.
Astronomer says.
Yeah, it's pretty insane. It's an unprecedented discovery. It's a new type of supernova that's super rare. I'd like to call it a naked supernova because we're seeing the guts of a star before it explodes. It tells us everything about how supernovas form and also like how we form, the atoms that make us up. This is pretty cool.
We're going to rate this episode MA because we're talking about naked supernovas. The byline on this CNN article, again, the story is coming out of a combination of institutions.
Yeah.
We have Northwestern, Caltech, and the Weizmann Institute. And the byline goes, astronomers have observed what they are calling a new type of supernova, which has provided an unparalleled glimpse into what happens deep within a star just before it explodes, right?
Yeah.
So this is like Taylor Swift's first album.
Mm-hmm.
We're looking deeply in.
Yeah, this is like the first album. Yeah, not all the random modern nonsense that she's doing now. Sorry. I'm a huge fan of Taylor Swift.
Yes.
But like when I was in high school and college.
Yes.
The new stuff not so much.
So we've talked about this before, and I think I have a little bit of an understanding. Supernovas are when these stars just explode.
Yes, at the end of their life.
At the end of their life.
Yeah.
But tell me more about what this story means, this research, and why it matters.
Yeah. So studying supernovas is extremely important for understanding not just like how stars live their life, but also like how we get the atoms that make us up. Okay? Because stars like our sun only create atoms up to the element iron. Okay. But the periodic table has a lot of elements after iron.
It's very large.
Every single element after iron was created in a supernova explosion.
Interesting.
Okay. And so understanding supernovas at a, granular level tells us something about like how these higher order elements formed.
We're trying to figure out all the ingredients.
Yeah.
And supernovas help us figure out a large set of those ingredients after iron.
Yeah. Supernovas are like the crucible for finding elements like gold, nickel, zinc, all of these things that are like pretty important for daily life on Earth, but also just for like making us.
Yep.
Right. And they're these stars are these cosmic crucibles, right? Like in the beginning.
In the beginning.
Yeah. In the beginning, after the Big Bang, there was only really two elements. Hydrogen and helium. Right. But clearly we're made out of a bunch of other stuff. Okay. Now, every element up to iron can be made by smaller stars like our sun. Okay. The sun can make stuff like oxygen, carbon, in very trace amounts. To get the real kinds of abundance that we see on Earth, you need bigger stars to make those kinds of elements.
Okay.
And then to get anything above iron, you need the star to explode. Okay. That's because there's something fundamental about the nuclei of atoms. Okay. Fusion, which is the process of taking lighter nuclei and fusing them to make bigger nuclei. So, the fundamental form that's happening in our sun is hydrogen, 4 hydrogens fusing to make a helium. Mm-hmm. And then helium can fuse to make carbon, 3 of them. That process requires the energy of the nuclei to be lower than the constituents that made it up.
Okay.
Because of the second law of thermodynamics, right? The energy of the stuff that was making up the product has to be higher. That way, like, it's thermodynamically more favorable to make that.
Makes sense.
Does that make sense?
You lose a little bit of energy when you
Yeah. And you want to, and the universe wants to dissipate heat because of the second law of thermodynamics. And so this process actually dissipates heat, which is fine.
Okay.
Great. The universe is like, you guys do that all you want.
Right.
Once you get to iron, fusing elements higher than iron means that you need to inject heat. Okay. So, and that's something that the thermodynamics doesn't let you do, right? Because second law of thermodynamics says that like the energy should go off everywhere, not concentrate into a single spot, right? The entropy should increase, not decrease. But this requires a decrease in entropy. And in order to get anything higher than iron, the energy per nucleon is actually higher, which means that you need a giant giant energetic event to actually start fusing stuff from iron to make zinc and gold and copper and uranium and all this other stuff.
This is why the explosion matters.
Yes, and this is why the explosion matters. Now, supernova, we've characterized supernova all over the universe, okay? The usual supernova is either a big star collapses, it can no longer hold its own weight, so it collapses, it explodes, and then you get this kind of stuff, right? And usually with supernova, you get to see the star as a whole collapsing, okay? This one is pretty crazy because like there were these intermediate stages where the star sort of shed its outer layers.
Okay.
And you got to see the real core of the star, right? And we got to see like the inside. And we got to confirm a lot of these models that we have about stellar evolution.
This is a really important point because, you know, our models are only as good as our observations.
Yeah.
That provide, you know, quote unquote, the training data for the models we create. And so as we start looking at stuff that we haven't seen before, it allows us to refine our understanding of the universe even more each time we see these new novel use cases.
Yes, exactly. The prevailing model, and it's I guess been confirmed by this particular supernova, is this thing called the onion skin model of big stars. Okay, what ends up happening is you got a big star. Every star basically starts off with about 75% hydrogen, 25% helium. Okay. Once you start off with that, the first thing the star does is the cheapest thing to burn is hydrogen. Okay, it's super easy. It wants to turn into helium. You just give it a little pressure and a little bit of heat, and it's like, all right, I'm going to go into helium. Now, pretty soon the hydrogen starts running out for these big stars within like tens to hundreds of millions of years. And then what's going to end up happening is the core is going to run out of the hydrogen. So it's going to start contracting because there's not enough hydrogen to push out. There's not enough fusion happening to push out the gravity pressure. So it's going to start contracting. As it contracts, the heat is going to go up, the pressure is going to go up, and all of a sudden helium burning is going to turn on.
Got it.
Okay? So now the helium is going to start burning into carbon and oxygen and things like that, right? And when that helium burning starts, the outward radiative pressure is going to get really big. So then the outside is going to expand, and that's when you get these red giants like Betelgeuse.
Yes.
Right? Or even the sun is going to end up doing this at some point.
Some French people were commenting on our pronunciation of
Betelgeuse. I don't respect the French. Yeah.
So whether you say Beetlejuice or Betelgeuse, we won, so we can decide how we say it.
Yeah. And you surrendered. Sorry.
Zebra, not zebra. But this onion model, celestial onions. And so this expansion of the outer shell.
Yeah. So you start expanding the outer shell and you become this like red giant, right? Yes. And then the core has like contracted though, and now it's starting to burn helium. Well, pretty soon it's going to run out of helium too.
Yes.
And then it's going to go into this thing called the CNO cycle, which is the carbon, nitrogen, oxygen cycle, where this like cycle between these three elements that's going to like start burning helium because carbon is a 12, oxygen is a 16.
Yes.
Right. So you're going to go from carbon. You're going to add a helium and then you're going to go to oxygen, but like iteratively.
Yes.
And so it becomes this like sort of like cycle of like trying to burn the fuel that you have. So the carbon is going to go, but then like that's going to start running out and you're going to start making silicon and like burning the silicon. And then there's going to be this iron core. So you have this onion skin model of all of these different processes happening in a star where the center is this iron that's not doing anything. Right outside, you have the silicon that's like burning. Right outside, you got carbon, nitrogen, oxygen that's burning. Right outside, you got helium that's burning. And outside, you got hydrogen that's burning. That's been the model that we know can happen from fundamental physics, right? We understand nuclei very well. We understand the atom really well. We understand the strong nuclear force really well. So we can like say, okay, these are the energy scales where these things happen. If I were to simulate this in a star, then it would happen at these radii because that's where the pressure and temperature is ideal for this kind of stuff. So this is the onion skin model, right?
Yes.
And we've confirmed sort of the outer layers of that onion skin. But like the deeper part, that silicon and the iron part, like that stuff's been elusive and it's sort of, we're just going off, well, we know how
the
stuff works, and we know how the nuclei works, so it's probably right.
Right. But now we've made this observational confirmation that this model that we have of the onion, of how stars create these layers, it has now been experimentally
because we've gone to the deepest parts of the onion. Somehow this particular star, it's called Supernova 2021 YFJ, because it was discovered in 2021. Somehow this particular supernova shed its outer layers through a process that we might get to later on.
Yes.
And so what we could see is the inside, that silicon part that we had never seen before. Yeah. And when they first discovered this supernova, they were like, what are those lines? What silicon? That's crazy.
Yes.
And immediately they knew that they had like a candidate for an extremely rare event. Right. And it was really exciting when they caught this in 2021.
So the idea here in part is that timing kind of matters. Like we caught it timing wise when it was at that stage when we made the observation. It was in this state that allowed us to see that. That more.
But the thing is, we've seen supernova with this timing before.
Oh, so this one is special.
Even rare. This is like special.
This is special.
This is a special supernova. They actually
interesting.
They actually calculated the event rate of this thing, and they said it was 30 per cubic gigaparsec per year. And that didn't mean anything to me because I don't really know. Like, I don't have I know what a gigaparsec is, right? It's 10 to the big parsec, which is like something to do with the parallax between the Earth going around the sun. And I was just like, okay, so how does this work? So I looked it up. The universe, the observable universe, is 30 gigaparsecs in diameter. Okay. So let's assume it's a sphere. So we'll say the radii is 15 gigaparsecs. That's the observable universe, right? Volume of a sphere is 4/3 pi r cubed. So 15 cubed is like 3,000. 3,000 times 4/3 times pi. Let's say the 3 and the 3 cancel. We're going to be engineers now, right? The pi is 3, like the engineers like to say. So then that's about 3,000 times 4. It's about 12,000 gigaparsecs, and then you've got this event rate, which is 30 per gigaparsec per year. So that gets you to about 300,000 per year in the whole universe. And that's actually insane, dude. 300,000. That's a countable number of zeros. There's only 5 zeros after the 3.
Countable number of zeros.
You know, like the universe is like what, billions of billions of trillions of stars and all this other stuff. Like, there's only 300,000 events in the entire observable universe in a single year. That's like actually extremely rare.
And so the idea is we really caught a needle in a haystack.
This thing was insanely hard and insanely rare, and we caught it because of some of the efforts that we've done in astronomy when it comes to this time domain astronomy. We had a previous episode where we were talking about the Vera Rubin observatory. The Vera Rubin is going to catch more of these things, right?
Right.
This one was caught not by the Vera Rubin observatory. It was caught by the Zwicky Transient facility. Okay. This is a facility that basically commandeered one of the observatories on Palomar, Mount Palomar, which is just south of us, near San Diego. It's a Caltech observatory. The Zwicky Transient facility uses a telescope that's much smaller and a camera that's much smaller than the Vera Rubin. But it was kind of a precursor to understand what are the challenges going to be when we make the Vera Rubin, right? You want to do, in science, you want to do baby steps. You want to be like, okay, let's start with, in this case, a 48-inch telescope, which is just like a little bit more than a meter. It's like 1.3 meter telescope. Compared to Vera Rubin's 8. And then the camera is way smaller. This thing started in 2017. And it does something very similar to the Vera Rubin, which is like go through the northern sky because it's in the northern hemisphere. It goes through the northern sky every 3 days. Every 3 nights, I should say. So it's doing sort of the same thing. So we could have a dry run on what the challenges would be for the Vera Rubin by operating this Zwicky Transient facility.
In the tech world, we always love to say, let's have a crawl, walk, run approach to this problem.
Yes.
And this is a very similar idea.
And this is exactly that.
You got to crawl first. Okay. what is the challenge to be able to walk?
Yep.
We walk, and now
we're running with Vera Rubin. Yeah.
Right. But there's an important point that the crawl or walk stages still have value.
Oh yeah.
In and of themselves, independent of the fact that we continue to increase our capabilities and these other tools.
Yeah. Yeah, it's. I mean, we always do this in science, right? We've got limited funding, so we better get it right. So you always want to beta test before you actually launch the product.
Right. If we're going to spend billions and billions, we want to make sure that it makes sense.
Exactly. Yeah. So the Zwicky Transient facility, it's been online since 2017, and this was caught in 2021. Okay, it was caught on September 7th, 2021, at like 9:56 UTC, and as soon as it was caught, they knew this was a candidate for something big.
Yep.
Okay. So immediately afterwards, that night, the Keck telescope, which goes online right after California, because Hawaii is like, basically downstream in terms of the night sky from us. Whoever was in charge of the Keck telescope, got the telegram or whatever, and was like, maybe my research can take a hold for a bit.
Yeah.
He pointed the Keck telescope there, and he got the spectra. Okay, because the Zwicky Transient facility at Palomar, it's only looking for changes in brightness. Okay, so it caught this supernova, which is basically, there's a bright star that appeared there that wasn't there before. The Keck telescope was like, I'm gonna point there, and it got the spectra, and the spectra was unlike anything you've ever seen before. Okay, it had lines of ionized silicon, sulfur, and argon. These are pretty heavy elements. Okay,
like
still lighter than iron.
Yes,
but pretty heavy.
Yes.
Okay. And this is something that we've like never seen before. The main thing was it also didn't have any hydrogen lines.
Interesting.
That's weird.
Yeah, that is.
Every star has hydrogen.
Yeah. So what's going on there?
Right? Every star has hydrogen, but this guy had like sulfur and like argon, but no hydrogen. So then they were immediately like, this is weird.
Yeah.
This is weird. So then there were a bunch of telescopes that worked together for 120 days after this explosion to just keep monitoring it. We had the Keck, we had the VLT down in Chile, we had the Lake Observatory, which is right outside San Jose in California, we had the Liverpool telescope in England.
Liverpool. Yeah. Little Scousers look too.
Yeah. And then we had the Nordic optical telescope as well in Norway. So we had all of these telescopes working in conjunction to keep track of this thing for 120 days. It was an incredible effort across the globe to try to just have like, full surveillance on this guy.
Right.
Because immediately from that very first spectra that Keck took, it was like, this is something new. This is something crazy.
Everyone drop your pencils.
Yeah, everyone was like, okay, this is... And it turns out it's a new type of supernova. We thought we had categorized the supernova. There's like the supernova where the star explodes. There's the supernova where a white dwarf starts siphoning mass from another binary star that we've talked about in an earlier episode. And then that white dwarf reaches a mass limit and then that explodes. So there's all these other types of supernova, but this had a signature that was unlike any other.
It was like a rare Pokemon. We ran up on Zapdos, Mew, Mewtwo.
Yeah. And as soon as we say, every human was like, okay, we gotta track this guy. We gotta see what he's doing.
I think one thing that's so interesting about this is it's a great reminder of the inherently collaborative nature of science.
Yeah,
because
in astronomy especially, dude.
Because we have to make observations, and necessarily because of planet Earth, and that we have different tools on different points on the sphere.
Yeah, and the Earth is rotating, so I only got like 8 hours of good nighttime.
Right. And then we're like, hey, you call up the Liverpool folks, like, hey, it's coming your way. Yeah. Click.
And they're like, okay.
This is really so this is a pretty, given we already have a really robust, and starting point in terms of already having theoretically and experimentally or observationally captured, a whole catalog of types of supernovas. The idea that we found a supernova that's like this 300,000 per year in the universe,
in the observable
universe.
That's insane.
Which, as we've talked about previously, is very large.
Yeah.
Very, very, very large. The opportunity again, this is rarer than Taylor Swift and Travis Kelce's engagement.
No, this is much more rare.
This is rarer
right?
than...
I don't know how many Taylor Swifts are out there in all the galaxies.
Yeah, right.
Right?
It could be quite a bit.
Yeah, there's billions and billions of galaxies.
Right.
Right? Billions of billions.
Billions of billions.
Like,
and
like
then
10 to the 9 times 10 to the 9.
Right.
Right? And then, but here there's like 300,000 of these.
Right. Which I know what 300,000 means.
Yeah, that's like I can visualize that.
Yes.
I can't visualize the universe.
Right.
But I can visualize that number.
Look,
That's insanely small for the universe.
Houses used to cost $300,000.
Yeah.
Right? And
They still do in some parts of America.
That's true. That is true.
Not in LA, I'll tell you that.
Southern California is not a beneficiary of that level of cost of living.
Yeah.
But exceptional discovery. Again, Northwestern,
Yeah.
Caltech, Wiseman Institute. So a little bit of everything. America heavy.
America heavy, yeah.
But a little international collaboration.
Yeah. There's also like a Chinese group because a Chinese group actually had access to Keck at the time.
Uh-huh.
And we were like, yo, this is dope. And they were like, yeah.
We'll move
Yeah.
it. Look, even given the geopolitical...
No, dude, everyone knows when you see like a supernova, it's like, let's just check its lines. And once they checked its lines, it's like, oh, this is a good paper. I'm gonna be on it.
It reminds me of like kind of how like anytime we talk about space, it sort of melts away the like,
yes. Yeah, because we're on a
sovereignty.
single planet and we're trying to make sense of whatever the hell is out
us.
there.
Right,
Yeah, right. Yeah,
right.
I think everybody who's an astronomer understands the speck of dust that we're on and the insignificance of all of these geopolitical conflicts.
Right.
When it comes to understanding a universe that is gigaparsecs on gigaparsecs big.
I think the first time I heard the word parsec in general was Star Wars. Because that's how they talk about traveling in between. It's 5 parsecs.
Yeah.
Let's do a jump drive.
Yeah.
Great story on the new supernova.
Yeah, it's an amazing dude, and I think it tells us a lot about like, first of all, like how we get the elements that we have.
Yes.
Right. It also tells us a lot about this onion skin model, the fact that we're right.
Yes.
Because it turns out so one of the questions is like, why are we seeing only sulfur and silicon, but we're not seeing hydrogen?
Yes.
It could be because like what's ended up happening is this star has been like pulsing, right? And as it pulses, it removes these outer layers, right? So that when it finally like exploded, the only layers that were left were these silicon layers, right? And so the light that we're seeing is coming through these silicon and sulfur layers, and then that's what we're seeing.
That's what I'm measuring.
There's still actually a mystery in this discovery. There were faint lines of helium and carbon. Okay. Which is weird because helium and carbon should be like out there.
Yes.
But we don't see any nitrogen, which should have been inside.
Yes.
Right. So like if we don't see nitrogen, that means the nitrogen layer is already gone.
Yes.
But like there's still helium.
So how did the nitrogen dissipate without?
And it's still a mystery. People think that it's probably like this thing is part of a binary star system.
Okay.
And then the star system, the other star, has a bunch of helium that like we're like seeing through, right? Because what we're seeing through is like the light coming from the supernova is like effectively like white light.
Right.
Okay. It's just pure energy from this collapse into an explosion. But like what the lines that we're seeing are the stuff that's getting in the way. Right. And so helium might be like this thing that's coming from the binary star. There's still a lot more that we can do from finagling the data.
Right.
But it's super exciting because it's a totally new type of supernova, right?
Yes.
Extremely rare. It's like nothing we've ever seen before. And it's great that it like confirms these models that we have just built on fundamental physics. Right. These are models based on just what we know about nuclei from experiments that we've done on Earth.
And we can
right, and it's insane that we can extrapolate from what we understand from the strong nuclear force and how protons and neutrons interact from what we've done on Earth to like then go all the way and see this thing that's like, half a megaparsec away, 120 days of data.
Right.
Yeah, it's really cool, the success, and that's what I mean when I say like, we're pretty good at physics.
Yeah.
This is what I mean.
Yeah.
We're pretty good at like making a model of a giant star that's 16 to 50 solar masses and be like, okay, it should be like a shell thing, because the gravity here and the pressure here means that the temperature is going to be at this much and the pressure is going to be at this much, which means that what I know about nucleosynthesis means that these are the kinds of elements that should be there, right? Like, we can trace all of these things just on a chalkboard. It's really incredible.
We love a good story that takes rare space-based events, connects it to the history of scientific discovery that we've already established on our little third rock that goes around the sun. And know that, oh yeah, we've been right.
Yeah. It's really cool. We've been right, and then there's some enigma, and that's probably because there's like some other thing that we're not seeing, you know?
And we have the tools to see it. Great. I love our space stories.
And I can't wait to see how many Vera Rubin is going to catch.
Oh my god.
Now that it goes online, like,
check out our episode 3 or 4, because we do a deep dive on it, and I
the greatest observatory
ever created by humanity to date. And I think about it a lot, actually. Every day I'm like, oh, did another
and you can just go online and check, like, what did it find?
The online Explorer is incredible. The data access, which we talked about, is incredible. It's for everybody.